Okay, welcome back, everyone. So it's a great pleasure for me to introduce my friend and colleague, Yichen Lou from the University of Western Ontario, and he's going to talk to us about asymptotic reasoning in black hole modeling and explanation.
Thank you, Martin, and thanks all organizers for this wonderful conference. My name is Yichen Lou, and I'm from Western University. Philosophy department and Rotterdam science. Sorry, I need to share the screen first. Oh, it's already shared. Before going through the talk, let's take some questions in mind in advance. So we talk about a lot of idealizations in economy, in like about ideal gas law, and also about things in social sciences. So let's ask, what are idealizations and approximations? What is distinction? Like, remember the Matthew's talk, he suggests that, well, maybe when we talk about idealization, we refer more to approximations, the idealization. And second, since the phenomenon we want to explain somewhat true claimed called explanation, how can models explain if they contain idealizations? And third is that, is it always possible to dispense idealizations or replace them with approximations in explanations? So in my talk, I think I have 3 parts. First, I introduce more about the main focus on this talk is the essentialist sensibilist debate on idealization and explanation. And I will try to peel the onion to try to find a common core of the idealization approximations and use the notion of asymptotic reasoning, and try to use this concept to define idealization and approximation and to reformulate the essentialist and dispensaries debate. In the second part, I will focus on the concept of asymptotic reasoning to argue that asymptotic reasoning itself is essential both in scientific modeling and scientific explanation. I will use the black hole modeling and explanation as a case study. And then in the last part, I will finally try to discuss the debate by using the knowledge and understanding of asymptotic reasoning. And once we are prepared, then we can go to debate to see what kind of possible positions we can take and what should we think of black hole models. Are they idealizations or approximations? Okay. I think Norton's paper in 2012 is a good starting point to define or to know more about idealization and approximation. To Norton, an approximation is an inexact description of a target system. It is propositional to the real system. But an idealization is a real or fictional system, distinct from the target system, introducing distortions in the system, some of whose properties provide an inexact description of some aspects of the target system. The crucial distinction is that only idealizations introduce reference to a novel system. For convenience, I think in this talk I will use the limit system to refer to the novel system that idealization introduces, and use the limiting properties of target system to refer to the description by approximation. And yeah, so let's take first an example to see the difference. If we want to explain, for example, how objects will fall on the table, and we want to explain this phenomenon, for example, a body of unit mass falling in a weakly resisting medium with no initial speed, we can do the explanation in 2 ways. First is through approximation. We can write down the full equation of motion in this form. And here K is a coefficient of the amplitude of the resisting medium, so that we can solve the complete solution for the equation. And because it is a weakly resisting medium, we can finally take the K, the coefficient, to be infinitesimal, to be small enough so that we can neglect some terms in the solution involving K, so that we get a final equation V equals to GT, which shows Y goes like a straight line. And all we can do this explanation through idealization. We can, from the very beginning, introduce a fictional system, a mass of the same size just falling under the same gravity in a vacuum. So in the very beginning, from the scratch, we neglect the coefficient k, so that we get a simplified equation. And solving this simplified equation, we also get v equals to gt. So they agree in this case. The problem is, when should we take k or take some parameter to be infinitesimal or to be a limit value? And that's a problem if we need a more complicated system. Recall that Norton warned us that if many philosophers talk about idealization, but in fact they are talking about approximations, right? And the problem is, why does idealization cast a worry in explanation? Why we should be more careful? And here seems attention for us. Our intuition shaped by, say, for example, representational accuracy or veritism of explanation. This kind of intuition suggests that there's no room for idealization, since it requires experiments to be true or approximately true. However, we know that idealization is itself widely used in scientific practice regarding modern explanation. So we want to make sense how idealization can contribute to explanations and what roles they play in different explanations. And back in 2002, Elgin and Sober already argued that, well, they can contribute to the explanation, but in a limited sense. They should be harmless in the sense that idealizations do not get in the way of those two parts of the model which do the actual experimental work. However, some others argue that idealizations actually play more important roles. And the classical example is the romanization group method explanation in phase transition. I'll just quickly go through the example. The technical details that do not matter here. So the critical phase transition happens if you have a system with enormously large degrees of freedom. And at a critical temperature and critical pressure, some interesting phenomenon will happen. For example, in the liquid vapor water system, you will see the boundary of gas and water or liquid begins to vanish. And there is also a really interesting phenomenon called a critical opalescence, in which you can observe the color of the system changes to be milky. And note that during this kind of critical phase transition, some universal behaviors, some universal patterns, just as I described, emerges across microscopically different physical systems. It can happen in the water system, it can happen in the carbon dioxide system, it can happen also in the ferromagnetism system. So in order to explain this phenomenon, we have our best scientific method called the renormalization group method. And Robertman argues that in this explanation, idealization is necessary and indispensable. So in this case, specifically, the idealization means the introduction of the number of components in the system to be infinity. It is necessary because this infinity enables us to locate the non-trivial fixed point at which those explanatory relations can be derived. However, many other philosophers use a perturbative analysis of renormalization group, and they found that, well, it is actually of no need to locate those fixed point. You only need the behaviors of the large but finite n system to that make it stay in the neighborhood of a fixed point. So the infinite idealization does not play essential roles in the explanation. This just gives you a sense about the classic debate, and different people can take different views about it. And to be more general, Shrek in his paper defines the essentialist and dispensablist debate as the following. He says, essentialist claims that some idealizations play a substantive role in science in the sense that they are indispensable for scientific account, including explanation of some physical phenomena. But dispensabilists maintain that idealizations play no substantive role in science and are dispensable from a true scientific theory. I think this definition is a little bit too general and not so informative in the sense that if we ask what do mature theories mean, if it means something about the future theory, that doesn't make a lot of sense because we don't know what future theory looks like, right? So I want to replace it with our currently best explanations and foreseeable future theories. We have some clues. And I also want to replace the substantive role because it's a little bit vague, I think, to replace it with some sufficient and necessary roles, so that we can have not only two positions, we can have conceptually possible more positions. And I just list four. There can be many, but those four are most plausible attitudes. The first is the strong dispensabilist attitude. It says that idealization is neither sufficient nor necessary for explanations, and only approximation is sufficient and necessary. And second is a mild dispensabilist attitude. It says idealization can be sufficient, but it's not necessary for explanations, and approximation is necessary. So you always need the idealization process to make you more phenomenologically informed. And the third is a mild essentialist attitude. It says idealization is sufficient and can be or may be necessary for some explanations of cases, and approximation in those cases can be or cannot be necessary. And the last one is a strong essentialist attitude. It says idealization is sufficient and necessary for explanations of some phenomena, and approximation is not necessary. Actually, I have in my mind already some philosophers who take different positions, but I think it's more important to just list those possible and conceptually possible views, so that you can decide which one you want to take, because people's minds are changing, right? Okay, so maybe you have already chosen one. So now, just want to think about it. As Norton wants us, we kind of sometimes mix up the idealization and approximation discourses. But how can it be possible, right? There must be, or there might be some common rule that connects those two terms. And here I just want to suggest a possible choice that's called asymptotic reasoning. It is something that scientists or physicists are really doing when they introduce assumptions or they are manipulating their modeling systems. So this is definition. Asymptotic reasoning involves investigations of limiting behavior of a system that is obtained when scientists assume some parameter can be increased infinitely or approach to infinitesimal value or reach a limiting value. This kind of method can be applied to manipulate the system's degrees of freedom, symmetry, overly intricate microscopic details, etc. So that we can simplify the calculation to derive the desired properties around the asymptotic regime where the phenomenon of interest happens. For example, in the phase transition case, we can understand that degrees of freedom in the system is taken to be infinity or taken to be increased indefinitely, depending on how you want to interpret asymptotic reasoning. And this is the case of asymptotic reasoning. And note that one of the strongest proponents of essentialist idealization, Batman, recognizes the significant uses of asymptotic reasoning in science. But it is also he who explicitly interprets asymptotic reasoning as idealization. The quote is from his book, Devils in Detail. Asymptotic reasoning, the taking of limits as a means to simplify and the study of the nature of these limits, constitutes the main method of idealization in the mathematician toolbox. And as we discussed above, however, there are some philosophers who also want to interpret asymptotic reasoning to be just approximations, right? So I contend that the essentialist and dispensabilist debate can be reformulated as a debate on different interpretations of asymptotic reasoning. So that essentialists are those who interpret asymptotic reasoning as idealizations, and claim that idealization play eliminable and essential roles depending on which position you want to take in the possible positions. And dispensables are those who interpret the simple reasoning as approximations and reject the essentialist claims. Also, to the degree they want the role of idealization plays. And by doing so, the merit is we can first focus on the roles of asymptotic reasoning in scientific explanation and modeling prior to entering the above debate. Before going into the case study, let me take some upshots from the critical phase transition case. There are two key features I want to call our attention on. In the phase transition case that make dispensabalist argument valid and more convincing in the philosophy literature. The first is that the phase transition phenomena are well observed within finite systems with enormously large components. So we have a lot of experiments, we have a lot of data, so that we can draw the figure as we showed in the previous slide. And second, there exists a well-developed perturbative analysis of the minimization group method. They can derive the desired properties from some finite systems to agree with those infinite properties of infinite systems. And the question now for the essentialists, are there cases where those features are absent, so that essentialists still could look for possibilities of indispensable idealizations, right? They want to look for a case which contains a lot of idealizations, and those above features are not less salient in those cases, so that they can have a chance for indispensable idealization. That is the black hole case I want to focus on. And here is the first image we scientists take from the corrected data. This is the first image in the human history, and the black hole picture is taken several years ago, and it's about a supermassive black hole in an 87 galaxy. And this image is shown in the units brightness temperature of photon. I will describe and explain more features of this feature in the explanation part. Now just give a sense of what black holes look like, and okay. And to study black holes, black holes mark one of the great successes of general relativity, and it is also our kind of best weapon to study black holes. And to understand general relativity in a nutshell, according to John Wheeler's summary of general relativity, that is, the space-time by its curvature teaches matters how to move, and the matters teaches the space-time how to curve. Right? By looking at the Einstein field equation, roughly speaking, it's not accurate, but roughly speaking, left-hand side are the curvature terms, and the right-hand side are the matter terms, the energy momentum terms. And one approach to study black holes is to solve the exact solutions of Einstein field equation to study the property of such space-time which contains black holes. And specifically, Einstein field equation has a solution, and this solution can be represented by this matrix. It has 10 independent components, too many. And these equations are really a highly nonlinear linear equations. So we need additional assumptions to reduce numbers of independent components to simplify the calculations. And we are going to talk about what kind of assumptions that employs asymptotic reasoning first in the static black hole, so-called Schwarz black hole. Reconstructed from Schwarz's original paper, we can formulate three assumptions which use the asymptotic reasoning. Some assumptions are more apparent that they use the asymptotic reasoning clearly, but some others are not. But I will explain later. The first assumption is about the stationality. Requires the Schwarz solution should be stationary. That is, all components we have seen of the matrix should be time independent. The toy model is like if I walk in a constant velocity and my motion of state is not dependent on time because the velocity is constant. Right? So it largely reduces the calculational difficulty. And the second assumption is about spherical symmetry, like the picture shows. It says there is a privileged orange, and the solution is invariant under the spatial rotation around O. And it also kind of simplifies the structure of the metric and simplify the calculation. And third assumption is the Einstein vacuum equation. Like vacuum again, vacuum always in physics. And it requires that the metric is a solution to Einstein vacuum equations, which physicists take the right-hand side energy momentum field to be zero. So that also we can largely reduce the calculation difficulty of such non-linear equations. And there's a theorem in general relativity called a Birkhoff theorem, states that if you have a spherically symmetric, that's by assumption 2, and vacuum solution is by assumption 3 in the external region, and that means this solution is necessarily static. Static means it's motionless, just keep frozen. So by doing so, by using those assumptions and those theorems, a structure solution can be represented as no cross terms appearing in its form, so that we only have 4 independent components now. And we need one more assumption to fix each exact form of the components. That is called asymptotic flatness. It says that the space-time we want to study should be asymptotically flat, like the space-time far away from the black hole, and it's just the flat form, like the Minkowski space-time. And this assumption helps us to have a boundary condition, and it introduces a physical interpretation of one undecided parameter of the metric solution from Newtonian physics. And that is, we can solve the term to be meaningful, to be physically meaningful. So, for example, the G00 then can be calculated as 1 minus 2m divided by r. The m here now means the mass of black hole. And sorry for taking so long, but we are nearly done. By using those above assumptions, we can now solve the Schwarzschild metric, and it is represented by this solution. I want to call on your attention on the red terms and the blue terms. Notice that if we plug r equals to 0 into each term, it's meaningless because it blow up, right? Go to infinity. And also, if we take I equals 2m in the second blue term, the second term becomes 1 over 0. So it also blow up for the component here. And specifically, I equals to 0 in classical black hole models means the intrinsic singularity at the center of black hole, while the I equals to m is called event horizon. Some more words about properties of the event horizon. By having those, by having the structure metric, we can use it to solve the trajectories of physical objects in this Eddington diagram. We see the real curved lines are the outgoing particles around black hole, and the dotted lines are the ingoing trajectory of an ingoing particle. And there are 2 properties of event horizon of our interest. The first is that within I equals to 2m, the event horizon, both incoming and outgoing particles cannot travel to the external part of the black hole in principle. And at I equals to 2m, particles traversing it from outside should keep moving constantly, keep moving smoothly without physical influences. They don't experience something real about the boundaries, not like a wall or something. You just go across it, nothing specific happened to you. And also, there are two important relations we want to derive from the structure metric. One is the condition for the event horizon. It shows the radius of such event horizon, such boundary is determined by the 2 times the mass of black hole. And also, it was mentioning that structure model yields an important observable prediction. There exists a so-called photon sphere, or so-called the innermost stable circular orbit for photons, ISCO, where photons are forced to move in circular orbits, and the ISCO relation for ISCO and the mass of black hole is given by the radius of the photon sphere to be equal to 3 times mass of the black hole. And inside the black hole, but outside the event horizon, right? We know event horizon lies at 2m, but the photon sphere is larger, 3m. Inside this region, this bound, there is no stable orbits for photons. So far, so good. But people may complain that, well, structure black hole model is really simplicity. It is a static, massive, and non-realistic model. But in the observation, we want a more realistic model, which is called the KEL model. It's rotating, it's not static. In order to derive this metric, it's not complicated. Now you need to relax the spherical symmetry to be axial symmetry. You just require there's a privileged axis, and the solution is invariant on the rotation about this axis. And by using the above assumption, A1, A2 prime, and A3, A4, we can derive the KEL metric from structure metric. And also the conditions of the event horizon and the condition for the ISCO can also be derived from KEL metric by this. Specifically, if we take the A is now the rotation or the spin of the black hole to be 0, the above equations reduce to those in structure black hole. That is, I equals to event horizon radius equals to m, and the photon sphere radius equals to 3m. Okay, sorry for the mathematics, but I hope it's fine because it's the basis of our discussion later. So the problem is, as I said, those assumptions imply a lot of a great deal of asymptotic reason. But how should we think about it? In other words, why should we think that above exact models or analytic models offer limit systems or limiting properties of black holes? And here's my criterion. One theoretical construct exhibits a limit system or limiting behaviors of a target system if and only if, first, the construct employs asymptotic reasoning that takes some parameter to a limit. And second, the characteristic properties can only be derived at or near this limit of the parameters in the construct. Then I'm going to argue that both structure black hole and KEL black hole satisfy the above 2 criteria and hence serve as the limit system of providing limiting properties of black hole in the universe. For example, the assumption of Einstein vacuum equation is a typical example of asymptotic reasoning because you just take the energy momentum mu to be 0, right? And also the asymptotic flatness A4, right? It requires the asymptotic distant region of the black hole should be flat, right? But there are some assumptions like sphericality and stationarity, which are less obvious to be asymptotic reasoning. But according to some mathematical studies of general relativity, there is a rigorous conjecture proposed by some mathematicians that if you have a space-time with initial small values, they will collapse. There will be some black hole formation, and those black holes will reach their final states, which look asymptotically like KEL black holes, KEL family black holes. And structure black hole and KEL black holes models are the members of KEL family black holes, which means KEL black hole and structure black holes are the final states and final stable states of some black holes in the universe. So that it makes sense now why we need stationarity and staticity, because in the final state, stable, so that the black hole is not moving violently, right? And also the symmetry. It is a final stable state of black hole, so they exhibit some really good symmetry. And furthermore, the asymptotic reasoning allows, as we have seen, that we can derive some desirable relations, for example, the event horizon condition and the photon sphere relation from those limiting stable black holes. So the conclusion for the first part is asymptotic reasoning plays an essential role in black hole model construction. And now I'm going to argue that, well, asymptotic reasoning also plays important role and essential roles in model explanation. And for the account of model explanation, I think Bockrich's account is very relevant and enlightening for my work. She requires that the experiments must make essential reference to a scientific model. And second, the model explains the experiment by showing how the elements of the model correctly capture the pattern of counterfactual dependence of the target system. So the model should be able to give information about how the target system will behave if elements in the model will change in various ways. So it's developed from Woodward's counterfactual account of explanation. And in addition, as Corey Rice argues in his new book, in many cases, idealization contributes to explanation by being first a constitute of the counterfactual dependence, and second, the demonstration of counterfactual irrelevance to experiment. Here I star mark idealization because we can replace idealization for now by asymptotic reasoning without loss of generality. And arguably, also in Woodward's 2018 paper, that the desirable counterfactual dependence together with a demonstration of irrelevance information, that is why other factors are irrelevant to the dependence relation, is what ultimately explains the experiment. Okay, so now what is the experiment of the black hole case? So we have this image, and there are three salient features of this image. First, we can observe that inside there is a near circular black region around the center of the black hole. And second, outside this black region, there the black hole is surrounded by a thick, bright photon ring. And the third is that the bright ring is asymmetric with enhanced brightness to the south. So those are the three salient features we want to explain in this image. And I believe some clever audience can already realize what kind of relations we already derived can explain this, right? For example, for the first point, we already have the existence condition for the event horizon, right? For example, in the Schwarz black hole case, it's I equals to 2n, right? And we already know some properties of event horizon that any physical particles once traverse the event horizon will keep falling inevitably toward I equals to 0, center of black hole. And nothing inside can escape to the infinitely distant observers, us, even photons. So it looks like black, right? And it's a circle region because the boundary is in black hole. In KO black hole case, is rotational symmetric. And second, we also calculate the ISCO, the photon sphere. In either model, it's easy to see that the radius of photon sphere is larger than that of the event horizon, so that there will be a outside black hole region. There is a thick, bright photon ring here. And to give a more precise explanation to the last two features, physicists introduced some simulation work which incorporate a turbulent hot magnetic orbiting disk into the analytic KELP model. The upshot here is that in this explanation, analytic black hole models play essential roles in simulation works and deriving counterfactual dependencies. And those counterfactual dependencies tell us not only why the phenomena look like the way they behave, but also the information about what makes or what causes the behavior in a way. Right. And this finishes the first part of the argument. Asymptotic reasoning in black hole models is constitutive of the counterfactual dependence in explanation, because all these counterfactual dependencies are derived from the exact solution of Einstein equation, and the metric itself can be solved only by using a lot of assumptions, which include the asymptotic reasoning. And now we can still ask, since the above analytic black hole models use a great deal of asymptotic reasoning, and so that we neglect some parameters and simplify the calculations, why should we think they provide adequate explanations, and why not just introduce back some neglected factors to make the black hole models more real? And this suggests that by understanding more about the irrelevance information, we can have a better understanding of the whole explanation. And luckily, this is done by the famous no-Hell theorems or no-Hell conjecture. Following two known physicists, Israel and Carter's work about the stability and rigidity of Kao and Schwarz black hole, three physicists proposed a generalized conjecture that the external gravitational and electromagnetic fields of a stationary black hole are determined uniquely by three parameters which can be observed by us: the mass, the charge, and the angular momentum. So we don't need more factors. We don't need to introduce more factors back to the black hole models. They can do their job nicely. So in sum, to capture the role of asymptotic reasoning explanation, I put forward the following argument. In black hole case, asymptotic reasoning is essential in deriving the relevant counterfactual dependence for the experiment. And second, asymptotic reasoning is also essential in providing insights about why irrelevance information does not make a difference to the experiment. And third is that counterfactual dependence and irrelevance information work together for explanation, and they are what explains. And the natural conclusion is asymptotic reasoning plays essential role, explanatory roles in explanation. So now we know some adequate knowledge of asymptotic reasoning, and now it's a good time to think about the debate, essentialist and dispensabalist debate. According to dispensabalist attitude, they want to interpret asymptotic reasoning as approximations. So if the above black hole models, if the above observed black hole image is explained based on the Kao model, the assumption of the Kao model should be approximations. And for example, we can think of the Einstein vacuum field equation assumption as approximation, because supermassive black holes keep absorbing masses into the black hole. So the density of surrounding universe can be thought as infinitesimal small compared to black hole. And also the symmetry condition can be the axial symmetry condition can be sort of also an approximation, because the black hole absorbs the moving bodies with angular momentum from different directions, and due to the conservation law of momentum, the whole system will behave like a spinning disk in ordinary celestial observation. And similarly, for the stationary stationary assumption, this also can be sort of approximation, because if a black hole reaches a stable phase in the evolution, it is a very good approximation to that state. Therefore, what the Kao model represents are merely limiting properties from approximation of black holes when they evolve for a great deal of time and approach to their stable states. This is a dispensabalist interpretation. Well, essentially, in response to those to the above interpretation, that the assumptions used in Kao model, Kao black hole model should be approximations, and the Kao model should represent a approximative state of the black hole evolution. And in response to the above interpretation, essentialists will invite us to focus on two features of classical black hole models. The first is about the I equals to 0 singularity. Now we have many singularity theorems which prove that the classical space-time models, if they satisfy some more generic assumptions, they must contain inevitably a singularity at the center. But it may encounter some contradiction from some advanced quantum gravity theory if they involve some microscopic quantum effect. For example, according to the string theory, there is a fast-Fourier model which says there is no such singularity inside black hole. Also, in quantum gravity, there is also no such endpoint of the space-time as singularity, but instead a small bounded region where the transition from black holes to white holes happen. And the second contradiction is by Hawking's work. According to the classical black hole models, event horizon, as we described, is a one-way membranes. Everything that traverses them is observed into the black hole, so that according to the radius of a relation between the radius of event horizon and the mass, the surface area can only grow. But Hawking's work by developing a semi-classical approach predicts that the black hole models will evaporate, leaving the event horizon to shrink. And this result suggests that classical black hole models, if taking microscopic quantum effects into consideration, they are not true approximations to our real universe. And essentialists may have more confidence to say that, well, they are idealization. Okay. These are their different interpretations, but how should we think about them? I think according to the interpretations we just discussed, that the difference between different attitudes in this space lies in the distinction, understanding, and requirements of first, the scientific explanation, and second, the views of truth. So I want to discuss first the strong dispensaryist attitude. If being a strong dispensaryist means that they require that experiments must be true or approximately true in the correspondence view of truth. The following is a dilemma for those strong dispensarists. Either they need to show how the conclusions from idealized model are proved relevant to non-ideal finite systems, like in the phase transition case. But this is not yet completely done in the black hole studies. Then, or they admit that their arguments are based on planned beliefs about the future magic fields. And also, another dilemma can be put for those sophisticated essentialists. Just want to record yesterday's talk by Dr. Potocznik that we can have different view of truth, and we may have a more plausible attitude toward understanding idealization and different kinds of realism. If those kind of sophisticated essentialists mean that they realize what ultimately explain other causal counterfactual dependencies, but due to the complexity of our world, we need to use idealizations for pragmatical purposes. And particularly, there's a pragmatist view of truth which is recommended to those sophisticated essentialists. And it urges them to stop thinking of idealization as strictly false. For example, Holly Anderson, in her forthcoming paper, proposes a view to replace the static and the once-for-all truth by a dynamic, constantly changing character of truth, of truing. And this truing view emphasizes the process by which models are brought into truth when they're target systems, and the fact that this process is not accomplished once and then it's done forever. but instead requires upkeep and ongoing fine-tuning, even in the best of cases. So if being sophisticated, if they listen to the suggestions by Professor Potocnik and Professor Anderson, and they want to hold that first, the counterfactual theory of explanation, and second, the pragmatic view of truth. And the following is also a dilemma for them. That is because they want to emphasize the idealization only on their academic roles in explanation, rather than their ontological status. And if sophisticated essentially is to hold such pragmatic view of truth and focus on the academically oriented roles of idealizations, they can just step back and interpret idealization as asymptotic reasoning without loss, because the academic roles of asymptotic reasoning already satisfies all the desirable properties of idealization they want. And it seems there is no gain for them to insist the idealization interpretation. Therefore, a faithful pragmatist essentialist can just pack the bags and leave the debate. So, sorry for taking up so much time. Thanks for your patience. Just some summary. So, in this talk, I reformulated the debate by the emphasis of asymptotic reasoning. I also point out that asymptotic reasoning plays essential roles in scientific modeling and scientific explanation in practical case. And also, I call for the attention on the academic roles of asymptotic reasoning by offering dilemmas for both strong dispensabilists and a sophisticated essentialist. Well, maybe it's not fair to say dilemma for essentialists because it's kind of a solution or the way out for this debate. And then the disagreements in this debate are less radical than we expect. Thank you.
Okay, so we have a little bit of time for questions. Yeah.
Mike. So thank you so much. This was really cool. Forgive me for still having ideal gases on the mind, but I'm wondering if you think that ideal gases are like, or the way we treat them is like a token of the type of like asymptotic reasoning that you're thinking of. Like, are they like are non-ideal gases approaching like a limit of ideal gas behavior? And if so, I guess this depends on which of the four positions that you are most inclined to endorse. But is that idealization or approximation? But I'm curious what you might think.
Yes.
So thank you.
Thank you very much. Right, good question. Thank you. Talking about my own position, well, I don't want to now commit to any position yet, but I would say I'm very sympathetic to the mild essentialist attitude. So that in this ideal gas case, I would prefer to think of it as approximation. And but notice that in this case, in this mild essentialist attitude, it does not require all explanations contain necessary and sufficient idealization. It just says that some phenomenon, for some explanation of some phenomenon, it can include some necessary and sufficient idealizations due to our knowledge of our currently best theories and best explanations. In the ideal gas law case, I think the explanation and the way we have the interaction between theoretical study and experiment are really clear, so that we don't have any puzzle or there is no any possibility that our understanding of the world and the theory will go wrong. So that in this case, I think the ideal gas model is an approximation. Yeah. Thanks.
Dr. Potocnik?
Thanks. This is a really clear and really interesting and useful talk, I thought. I appreciate it. remember how to talk to you and be on camera at the same time. I'm glad we're on this slide. This is helpful for what I wanted to ask about, which I can't resist is going to be about that sort of strong essentialist view that you walked us through the difficulties with at the end. So I wanted to ask or float the idea if there isn't actually a kind of advantage to landing in strong essentialism land versus mild essentialism. And here's what I have in mind. If I compare the two statements of them, it seems like what's different between the two. So I feel, sorry, backing up slightly, I feel the pull of the concern that you raised that if we're sophisticated, and you and I talked about this offline as well already, if we're sophisticated about what it is that we're requiring of a positive truth, then it seems like if we get strong enough in the sort of epistemic value that we're attributing to an idealization, what we're saying just should be that it's effectively true or something like this. But what I see as the big difference between 3 and 4 looks like is about this approximation claim, right? So the strong essentialist, if I'm understanding this correctly, will sort of grab on tight to idealization as really important to scientific explanation, I gather, and push approximation to the side. Maybe it's there, maybe it's not. So sorry, I'm wordy. I'm trying to be as brief as I can here. So what I want to ask about is whether, if you have this sort of a view, or I suppose that sort of a view, I think, might be supported by different styles of idealization and explanation. So jumping to a different scientific context for idealization, the assumption that a population is infinite, right, in biology, which is employed, it's the sort of causal facts are really different from this example in that there are all sorts of real features of evolved populations that result in genetic drift being an important influence. And assuming the population is infinite is just a way of sort of wholesale brushing all of those probably causally relevant on the outcome influences to the side in order to focus in on selection in particular often. Whether we think the population, whether we have any reason to think the population, in fact, is one, or the evolutionary outcome is one to which drift wasn't important. So I wanted to sort of raise that different example because it seems like one where, unlike in the case you walked us through, approximation can't be used as a substitute or a sort of close relation to the role that idealization is playing, because it's sort of more crucial in that case that we are sort of subbing in something, simplifying for factors we just don't know anything about, versus that we have reason to think don't matter, something like that. And I'm going on for too long, so I'll stop there.
I hope I understand the question.
Yes.
Thanks very much. That's very intriguing. First of all, I need to say that all the idealizations or the definition of sympathetic reasoning so far is suitable for the physical idealization, or physical approximation. But I also want to think about more idealization in like biology or the social sciences, so to make it more general. And talking about the population idealization, I don't know so much about the evolution biology, but I think it's not contradictory to the third option, right? Because it emphasizes the academic roles of this assumption, which help us know much better than before, right? So we know the behaviors, the causal patterns in the evolution biology, and that this idealization really helps in the sense that they provide academic values. And the question is, if I understand right, that then what is the distinction between idealization and approximations, and does it matter, right, in the specific case, which is really a good case for idealization. Yeah, I think it depends. Actually, this kind of discussion depends a lot on the knowledge of the case study. So maybe I need to say I'm not really know how to answer your question, but I need to study more about that case in order to give you a complete answer. Yeah.
Okay, thank you.
Thank you. Thanks for the question. Yeah.
Other questions? Robert DeSalle, go ahead.
Hi. Thanks for that was really an excellent talk, and
Thanks.
I'm not sure. I thought it was especially interesting that you showed some of the usefulness of Professor Patočnik's ideas too, as well as relating it to general relativity and black holes. I have a small question that, excuse me, for clarification, that isn't hostile at all. But one of your later slides, you made a distinction between well, let me put it another way. You talked about how finding counterfactual dependencies helps to explain why or the causal relations. Excuse me. So I was just wondering if those two notions were sufficiently distinct.
I'm sorry.
It must have been. It was a slide a few times before this when you first introduced the idea, showing how counterfactual dependencies explain why.
Oh,
Great.
the second and the third, right?
Yes.
Yeah. Well, maybe it's not third one, but it's a supplement to the second.
I mean, if they're totally distinct things, then we could say perhaps one is explaining the other, right? In the sense of giving a kind of ground for it. And if we didn't distinguish them, then we might want to say something different, like that the account using an idealized model by explaining counterfactual dependencies gives content to the notion of a causal dependence. So I'm not sure if I'm making myself clear, but the distinction between a kind of an analysis of what causal explanations really do versus a ground for a causal explanation.
I think, so first of all, this is not the original code I take from Brokerage, so I take a pen. And second, I think maybe, you are right that there might be a further step for explaining causal patterns or counterfactual dependence. And here, maybe the third requirement is stronger in the sense that it increasingly uses the interventionism, in the sense that, well, you need to, in principle, theoretically possible to change the values of the say, for example, the mass of black hole, so that we can see the changes of the event horizon. So maybe yes, there's a sense that the third one is kind of independent from the second one, in the sense we I suppose some interventionism here.
Yeah, I don't think this is the slide I was thinking of, but I think I see what you mean. It's okay though. I don't want to take up too much of your time. I think I understand. Thanks.
Thanks.
We have time for one quick question. Okay, let me abuse my power. Can you go back to the slide about the dispensablist dilemma? One of your last slides.
This one.
A dispensablist.
Oh, sorry.
Yeah, so I guess I don't quite see why this is a dilemma and why a dispensablist wouldn't just take the second horn.
The second position?
But not in the way you phrase it, right? So don't we have lots and lots of good inductive evidence that the idealizations we use end up as approximations once we have better techniques at
Good. Yeah, but as I discussed above, in the specific case, where are your inductive bases, right? For example, I already mentioned some theoretical contradictions. which might include, which might lower your credits about your claim, right? So there are many theoretical contradictions to our better theories, maybe better theories of continuity or something like that. And it shows the classical models might not be approximation, or they might be wrong in the sense that they don't consider the quantum effects. And also talking about the better method, but the perturbative method, yes, we are going to, mathematicians and physicists are developing some kind of perturbative method of generativity, but it's not yet been done. And also, they developed some kind of track surface notion and apparent horizon so that we can to think of the event horizon in a more dynamic way. But the problem stabilizing the contradiction of the classical GR, because they talking about this kind of black hole bodies, they already have some contradictions which can largely reduce your practice of the future theory or future with the idealization process.
Okay, thanks.
Thank you.
All right, let's thank Yichen.